is to try to explain calculus. I'm going to do this in two ways. One is a sort of very long-winded way, about 20 minutes or so, that will give you an understanding of kind of why it works. The other way, which is at the very end of the video, so skip there if you want that, is called the sort of power method, and that's the way we just do it in practice, and the way you would quickly get to what the derivative of an equation is. But the first part will explain in a bit more detail why it works, for those of you that need to know why it works. So if we begin, we're looking at the problem of curves, the gradient of a curve. For those of you that skateboard, you'll recognize this. We have at the bottom of the ramp, if you like, a horizontal section, at the wall of the ramp, a vertical section. Those bits are obvious because they are, of course, their gradient is vertical and their gradient is horizontal. It's this transition in between that causes a problem. And what we recognize, from skating or from just walking up a hill, basically, is that there is a transition. And that transition means that the gradient gets progressively steeper and steeper and steeper and steeper and steeper. It doesn't have a single gradient. It's not like going up a slope with a constant gradient. There's a constantly changing gradient depending where we are. That, of course, is how that works on a skateboard. If this was a straight line here, what would happen is you would hit this so quickly coming down basically the board would kind of jump out from underneath you, as it were. It only works because it's this smooth transition of constantly changing gradients. The same thing appears on a graph. A flat section here, a steep section here. For those of you that look at economics, you're looking at sort of a very elastic section here and a very inelastic section here. But basically, a constantly changing gradient. There's our problem. Make it nice and easy. Let's have a look at a straight line. With a straight line, what we look at is a change in x and a change in y. So we normally look at the change in x value, change in y value. We divide the change in y value by the change in x value, and we end up with a gradient. So basically, change in y divided by change in x. I've written it in a little bit of a fancy way here. There's a reason for that. That'll help us in a minute. But basically, change in y, change in x, and we can refer to that as m. We can look at that as a gradient. For those of you that have done some stuff on the equations of straight line before, then you'll know that the equation of a straight line can be given as y. The y value equals mx plus 1. So the y value is the gradient multiplied by the x value plus constant. Sorry, did I say plus 1? I meant plus constant. In our case, the constant would be 0. So the equation of this straight line is y equals mx plus 0. So y equals mx. If this line intercepted the axes further up here in the positive values, it would be y equals mx plus 1, 2, 3, 4, 5, whatever number. Likewise, if it intercepted it in a negative value, it would be y equals mx minus, to show me starting at a lower point. If the line sloped downwards, it would be minus mx, just a negative gradient. Okay, so the one takeaway from this, though, is this idea of writing y2 minus y1, x2 minus y1. That's what x2. I want to take that away from this. Yeah. It also turns out, by the way, that if we do tan of the theta value, is basically you can work out what the angle is as well. But again, that's not important at this second. So one of the ways we can think about this is, well, hold on a second. Let's look at a curve as if, let's pretend it's a straight line. Take an average. An average will work for us. Yeah. So in our case here, we're going to pretend, as it were, there's a difference of 2 here, which is a strange axis on the bottom in that. Strange scale on the bottom, but we'll go with it. And a difference of 2. That was a frightening page, wasn't it? A difference of 2 here and a difference of 2 here. We would end up with 2 divided by 2, which is 1. So we can say, well, the gradient of the curve at this point is kind of 1-ish. Okay. Again, if this was different values here would present different gradients. It's okay, but come on, that's not the gradient at this point. That's kind of an average gradient over a couple of points, and even that's not right because it's a curve pretending to be a straight line. But it's an idea. But maybe if we make the gap smaller, so we'll try it again with a smaller gap. Let's do it again. Smaller gap this time. Okay. Same equation, y equals x squared plus 1. Okay. I brought the line up here to represent we're coming up the axes a little bit. And if we said the point P was 2 and a 5, okay, so there's a 2 there for P and a 5 there for Y. That's the first point. That's XY. If we increase X by 0.3, we're going to get a new Y value of 2.3 squared plus 1. Okay, so the new x value is 2 plus 0.3, 2.3. We square it, we add 1 to it, and we end up with a new y value. So the new x, 2.3. The new y, 2.3 squared plus 1, 6.29. So now we have a new position. We can say that y is a function of x plus dx. So I skipped over that a second ago. Apologies there. You notice at the beginning, too sensitive a mouse. You notice at the beginning I had y equals fx. For those of you not familiar with this, when you see y equals fx, it's not asking you to do something mathematically. F italicized f just means it's a function of. So y is a function of x. The x, instead of x now, I could have, for example, if I were looking at student grades, I might have grade equals f, open brackets, attendance, hours spent studying, previous academic results. You know, the parts inside the x are the independent variables that are forcing the y to move. Okay, but it's not. This is not at that point a mathematical function. You certainly don't multiply f by x. That's not what that's saying. That's why it's in italics. It's just saying it's a function. So what we're suggesting down here is y is a function of x plus its friend, if you like. Yeah, this change. So the 2 plus 0.3. 2 plus 0.3. Okay, so we're pushing it, we're nudging it along, and that's making a difference. Apologies again. I need a less sensitive mouse pad. So point Q then is 2.3 and 6.29. If we divide them through, we end up with a gradient of 4.3. So we've squidged it down and we found out a gradient of 4.3. This is a little bit of a different graph than the previous page, of course, because this one starts at 1 and bits and pieces like that. But anyway, you can imagine I can keep doing this. I could go to 0.2, 0.1, 0.01, 0.001, 0.001, and just keep going. I can make the gap smaller and smaller and smaller. And as I do so I'm getting kind of closer to what the gradient might look like. Okay, so weirdly with averages, usually we try to increase numbers, don't we, to get closer to a proper increase the sample size to get closer to the population. But in this case, of course, if you like, what we're trying to do is to get smaller to get closer to that single point of change. So single point of change. We're at that specific point. We're looking at the change. All right. So a little bit more of a way of writing stuff now. The equation here in front of us, look, we've got this dy dx. The dy, change in y, dx, change in x. Okay, so we're just saying the change divided by the change. So the change in y, the change in x. The change in x, of course, is just the change in x. That's the independent variable. But the top part, what we're looking at is the original position, the original place where x was. F is a function of x, in our case x squared plus 1, but it could be anything. It could be x to the 7 plus 42, it could be anything. In our case it's x plus 1, but that's the first part in green. That is showing us original position of y as a function of x. Sorry, nothing to do with that one down there at the moment. That's me getting excited. The original position of y is basically a function of x. And of course, the new position of y is a function of x plus the change in x. Okay, so x plus dx. So fx and fx dx. Okay, so just a change, fx plus dx, sorry. The change in the x value has created a new y value. So the change in y is explained by the change in the original y position, sorry, over there, original y position and new y position. All right. Again, there'll be a reason why I've written it in this rather strange way. We're just going to walk through a series of steps like this that allows us to understand why we actually can get to a gradient from playing with these smaller bits. So, same equation, just added a little bit in it down here where I've got this limit dx arrow 0. Okay, what we're saying here is the limits as dx approaches 0, as dx tends to 0. I'm now suggesting that this dx value on the bottom of my equation is going to be really tiny, really tiny, almost to the point of being 0. And what we're suggesting here, is obviously I can keep drawing lines. They're all going to be slightly different gradients, aren't they? But the closer I get in, the more focused I get in towards this specific point, the change in x value will get closer and closer to 0. And as such, well, the change in y will also get closer and closer to 0. It'll certainly have less effect, won't it? The smaller the change in x, the smaller the change in y. But we're going to approach then what this minuscule little flat line will look like, which will enable us to work out the gradient. Just playing with some ideas. If I was to take this as a zooming in, I'm afraid my animation isn't that great, so I've had to do it like this. But if I was to zoom in to a curve, if I keep zooming in, you can see the line begins to look straighter and straighter. think about the planet. Yep, you're in a room at the moment. I'm sure the floor looks flat to you. I'm sure if you look outside, the world looks kind of flat to you because the world is flat. Well, it's not flat, is it? We know that. That's nonsense. The world isn't flat, but in our perspective from where we are and where we exist wandering around it, it appears to be flat because we're tiny. It is tiny, the area of the world that we can see. Thus, it looks flat. That's exactly what we're doing with these curves. We're zooming into such a point where it will appear flat. And of course, the globe isn't flat. It's clearly not. But from our perspective, our zoomed in perspective, it just as well be flat. This is how it's possible, to build houses and roads and bridges and various other things. We don't really need to take into account the curvature of the Earth because we don't build things big enough to worry about that. Someone will probably correct me in the comments there. I'm sure there is stuff we do need to worry about when we build. But for most intents and purposes, we don't have to concern ourselves when we're laying out the foundations or the footings for a house. So we are so zoomed in that it is effectively flat. So, quick recap. You can get the average gradient of a curve by taking 2 points close together, just like it's a straight line, or if you zoom in, it gets more accurate. We call the equation of a curve y as a function of x. In fact, we could actually call the equation of a straight line y as a function of x, I suppose, technically. We use dx to mean a change in x, dy to mean a change in y, and we call the second point, the new value of y, fx plus dx. Okay, the dx bit representing this slight change in x, and dy dx is the gradient. Okay, so starting with our original equation, I want to focus on that bit in red there, the x squared part. Okay, focus on this bit because that's the bit we're going to play with for a little bit. So we then said, now notice I've got this little tick. I'm starting to play with the idea of this being a derivative, as it were. Okay, so that's what that little tick starts to mean. So we're starting to play with this part here, this change in x value. Okay, so we're going to change the x value a little bit. And if I look at this, what I'm effectively doing is I'm going to drop this bit, x dx, into my original equation up here, x plus dx squared. Yeah. So if my x was 5 and my dx was 0.1, then it's going to be 5.1 squared, isn't it? Yeah. So that's all I've done. I've just taken that part and I've dropped it into the original equation, replacing the x with an x plus dx, x plus whatever my tiny change is. Okay. So that's the first trick. Then what I'm going to do is expand the square. Okay, so x plus dx is a square. It's x plus dx squared. I can expand it to give me x squared plus 2x dx plus dx squared. Now, that might be obvious to you, and if it is, you can sort of jump over the next minute or so. If it's not obvious to you, I'm going to try and explain to you how you expand the square so we get to that point. Starting then back where we are, same thing, x squared plus 2x dx plus dx squared. There's a lot of x's going on in this. X plus dx squared is effectively the same as x plus dx times x plus dx. Now we can use a technique called FOIL where we look at the multiplying the first two terms together, the outside terms together, the inside terms together, and the last two terms together. That's how we expand a square in this instance. So the first two, what have we got first of all? We've got two x's. Okay, well that'll make x squared, so x times x. The outsides, x and dx, yep, there's an x and there's a dx on the two outsides. That makes x dx. The inside, we've got a dx and an x, funnily enough, exactly the same thing. So that makes a dx times x, which is x dx, if I just rearrange that slightly. And then the last one, of course, is dx dx, which, of course, is dx squared. So now we have ended up with x squared, x dx, and dx squared. Altogether then, x squared, x dx, dx squared. Well, of course, that's just two of those, isn't it? Look, 1, 2, I can count that easy enough. So what we've ended up with is x squared plus 2x dx plus dx squared. All right, that's how we got to that. One might almost ask why, okay, because all that's happening here is we're making it longer and longer and more complicated, but it's going to enable us to do something in a second, and there is only a couple more steps, people, and we'll be able to get to the answer to what is the equation of this curve. So, there's where we began here. Yep, all right, we said we're going to replace this x plus dx with what we've just expanded, and that allows us to write fx plus dx is x squared 2x dx plus dx squared plus 1. Just tagged on the 1 because the constant needs to be tagged on the end. Okay, so there's what we just wrote on the previous slide. Can we figure out what mx is? Can we figure out the change in x given this? So, no, that's interesting. So can we use this to work out what the change in x is? Well, let's try that a second. So if we first of all bring down the fx here, okay, so this is the change. We're going to look at the difference, if you like. Yeah, there's the original position, the change in y. Sorry, apologies, change in y. There's the original position of y. There's the new position of y. Let's bring that down and bring it down over here too. Okay, so taking this one, look, and then I'm just going to minus fx from both sides, though in this case I'm writing x squared plus 1. So these are the original positions of y taken away from the new position of y, the new position of y. But that's handy because I can start cancelling a few things out. Look, I've got an x squared there and I've got a 1 there, and magically I've got an x squared and a 1 there. So they're all gone now. Boom, like that, okay? Leaving me with fx plus dx is 2x dx plus dx squared. Okay, so fx dx minus fx, 2x dx plus dx squared. So phew, we're starting to reduce down the number of terms in our formula, in our equation. We were expanding them for a while now they're coming back down, they're reducing. If we look at the top, okay, 2x dx plus dx squared, that is effectively the same as 2x dx and dx squared. Yeah, plus, and it's the same sort of thing. Arguably, same sort of thing. Dx is common to both. So what have we got? We've got dx times 2x, if I just times that out, and I've got dx times dx. I can write it like that. That's interesting, because that lets me write dx 2x and dx dx. Okay, in this way here with the brackets. Well, actually, that can be written much simpler by simply writing dx 2x plus dx. So I can simplify the part on top here to simply dx 2x dx. If we times that through, you'll get back to where we began. We will back to this if we multiply this through. So that's kind of useful because we now end up with this. Well, you can see here, this is looking like an opportunity, isn't it, to start dividing things. So let's try that. We'll divide that. Well, yeah, we can get rid of that, can't we? Because we're dividing it, we're timesing it by dx and then dividing it by dx. So let's just lose the dx. We end up with 2x plus dx. Cool. Okay, this is getting much simpler now, isn't it? But actually, we said dx was so tiny, it kind of just as well be 0, which seems to sort of suggest that actually the gradient of this curve can be found by using 2x. So at its limit, the gradient is effectively 2x. Okay, how would that work? Well, what we can do at this point is plug in any x value and it will tell me the gradient at that specific point. So x value of 10, obviously the gradient would be 20. We just plug in a different x value and we'd be able to get the gradient at that particular point, or we'd be able to plot the curve or whatever you wanted to do. Okay, so that's interesting. We've had this sort of like journey, if you like, of just making assumptions and playing with the idea of tiny spaces, and it's dropped out the end the idea that the gradient of the curve at a particular point can be given by 2x. Obviously, these values would be different if I began with a different formula. If I was x to the 3 plus 7 or something, or whatever, we would end up with a slightly different answer, but nevertheless, we would end up with an answer following the same process. Quite long-winded, I'm sure you'll agree. So let's have a little play now. This is the fun part, if you like, yeah? So we said x squared plus 1 is, the derivative of x squared plus 1 is 2x, okay? After those bits of fun maths, okay? We ended up with that. But I'll let you into a secret. You may have already known this, okay? A bit of a secret. There's a thing called a power rule. The power rule tells us that the function of x is where if we look at it as x to the power of n, and I'll explain about the constant in a second, but x to the power of n, then the derivative of that is the x value multiplied by the power, and then the power reduced by 1. So in our case, it was x squared. So x multiplied by the power, squared is a 2, so that's 2x, and reduce 2 by 1, we end up with 1. We end up 2x to the power of 1, which of course is 2x. If it was x to the power of 3, yeah, we would have x multiplied by the power, which is x times 3, that's 3x. Reduce the power by 1, okay, that's 3, that becomes 2, so we'd end up with 3x squared. Okay, if we began with 2x to the power of 2, it would simply be 2x multiplied by the power, so that's 2 times 2 is 4, 4x, reduce the power by 1, 4x to the power of 1, it would be 4x. Okay, so you can see it's nice and straightforward. The derivative of the constant, you know that if we just like create a sort of this fictitious x value, okay, x to the power of 0 we'll call it, which is 1, so x to the power of 0 is 1. If we then multiply our constant by x to the power of 0, so imagine I've got plus and there's a constant sat out there. Ours was actually 1, wasn't it? So we would end up with plus 1. Now if I said, okay, that if I put x to the 0, 1x to the 0 if you like, that would be 1 times 1, which is still 1. Now if I was to times 1x by the power, I'd be timesing 1x by 0, and as you know, 1x by 0 becomes 0. So the constant becomes 0 because if we were to assume x to the 0 is in there as a 1 value, then it's always going to reduce down to 0. And so the constant is 0. Or you can just ignore the constant. Okay. Looking at our example, then we have x squared plus 1, x 2 minus 1, or 2x, sorry, 2 minus 1 plus 0. And yeah, we end up with the simple sort of 2x value there. So basically that's it. Yep. Okay. So just ignore the constant and drop the ignore the constant, times the x by the power and reduce the power by 1. You can do this a second time. You have like a second order if you like. Okay. So you can do it once more. Follow the same instructions. Reduce the power. Sorry, multiply the x value by the power and reduce the power by another 1. That's the second derivative, and this is looking at sort of acceleration, if you like, and direction of rates of change, whether things are increasing or reducing. So that can be quite interesting. There's also integration, which is the area under a curve, and for the area under a curve, you effectively do this in reverse. So you divide the value that you have by what would sort of, well, let's just try and do it with the one we've got in front of us here. Should we do that? Okay. So if I do 2x, I would end up with, well, the power increases by 1. So I've got 2x to the power of 1. That becomes 2x squared. I then divide it by the 2x squared divided by 2. Of course, just leaves me with, the 2's cancel out. It leaves me with x to the power of 2. Okay, so you kind of do it in reverse. That'll be a whole different subject. We can do one on integration if you want to. That looks at the area under a curve by assuming that the curve is chopped up into tiny little rectangles, so tiny the tops of them are effectively flat. Okay, but like I said, we can look at that another time. Drop a note in the comment if you want me to have a look at that. Otherwise, like I said, like and a follow and all that sort of things is always lovely. Anything else you'd like me to have a chat about, just let me know, and I'll see what I can do. But thank you for listening.